Um, yeah, so thank you so much for the kind invitation to present my work here at Amplitudes 2025. Um, what I'll be talking about is very closely related to what Sylvia was talking before, and this has to do with the loop level. So I'll be talking about some work that has culminated over the last couple of years with my collaborators Alok Lada and Andrea Pum. So the title of the talk is Classical Logs of Graviton Theorem from BMS Superrotations. I'll describe what these are in a minute. This has to do with the relationship between the soft theorems and asymptotic symmetries. And Sylvia has given a review of what asymptotic symmetries are. And I'll just do a lightning review in one slide. So a nice way to think about asymptotic symmetries is that it's the allowed symmetry group modeled out by the trivial gauge symmetry groups. So what I mean by this is not all gauge transformations are trivial. And of course, there are gauge transformations that are disconnected from the identity, but these are not what I am referring to here. If you follow the Noether procedure to compute the charges that generate gauge transformations, you'll find that in order for this to vanish, you do a partial integration in the computation. And when in order to make the boundary term vanish, you impose certain fall-off conditions in the gauge parameter of the symmetry. And actually, if you look at the allowed fall-offs of the fields, the fall-off condition that makes these charges vanish is a little bit more stricter. So there's a little gap in the allowed parameter space, which is still allowed physically, but these they fall off too slow for the gauge field for the charges to vanish. And if the charge doesn't vanish, it has a non-trivial action on the states, and therefore these transformations, even though they're formally gauged, they are physical. And something that will be relevant for my talk is the asymptotic symmetry group of gravity in asymptotically flat spacetime. And by asymptotically flat, I mean the spacetimes that fall off at infinity to be flat. And in this case, you'd want to guess that maybe the asymptotic symmetry group would just be Poincare. But actually, people have worked out the symmetry group in the 60s, and it turns out that it is a little bit more than Poincare. The symmetry group is called the BMS group, named after the authors Bondi, Metzner, and Satz. And this group is an extension of the Poincare group, where we generalize space-time translations to be an angle-dependent time translation that is referred to as supertranslation. And unfortunately, we have the word super here, but this has nothing to do with supersymmetry. This is just a generalization of translations. And in the last 10 years, the Lorentz transformation has also been generalized. There are two different ways to generalize this, and they are called superrotations, but I will not go into details here. But these extensions are usually referred to as the extended BMS group or generalized BMS group, depending on how you generalize Lorentz symmetry. And these asymptotic symmetries are symmetries of scattering processes. And what I mean by that is the charge of these asymptotic symmetry transformation is preserved if you compute it from incoming state to an outgoing state. Right? Now, over the last 10 years, a remarkable correspondence between soft theorems and asymptotic symmetries has been uncovered. And some of this was also noted in Sylvia's talk. And the correspondence is this. A soft theorem is nothing but the word identity or the statement of charge conservation of an asymptotic symmetry under scattering. So this charge conservation law is a clever rewriting of a soft theorem. And this has by now been studied in many different cases. For instance, the large gauge transformations in QED, its word identity corresponds to the leading or Weinberg soft photon theorem. In gravity, the BMS supertranslation, its word identity corresponds to the soft graviton theorem. And even more, the BMS superrotations at tree level corresponds to the subleadings of Graviton theorem. And Sylvia has mentioned these divergent large gauge transformations. These one can show at tree level is the subleadings of photon theorem. And this extends to higher dimensions, to theories with supersymmetry. So although this correspondence is studied on a case-by-case basis, it seems to be very robust. And because my talk will be on this subject, I'll just illustrate how this happens. And just for concreteness, I'll do superrotations. So the leading and subleadings of Graviton theorem can be written in the following form. So the n+1 point amplitude with the graviton, if you take the graviton energy to be solved, there's a pole times the Weinberg-Self vector plus the subleading Self vector that is independent of the this energy at tree level. And if you compute the superrotation charges in the past and future infinities via the covariant phase space method, they usually split into a hard and a soft part. The hard part has to do with the matter fields coupled to gravity. The soft part has to do with contributions coming from graviton. And then we choose a specific vector field such that the action of the hard charge on the states is precisely the subleading soft graviton vector. And then the soft charge has to do with an insertion of a graviton in the soft limit with a particular projection in the energy space. So the charge conservation law is basically the sum of these two things. And it turns out to be that a graviton insertion in the soft limit with a projection is equal to the soft vector. And this projection works in a way that precisely picks out this omega independent term in the soft expansion. And therefore, you can see that the conservation of the statement of charge conservation of superrotation corresponds to the subleading soft graviton theorem. Now, in 2014, Sweburn and his collaborators, Davis and Knoll, have shown that the subleading soft behavior of gluons and gravitons receive loop corrections. Specifically, if you use IMREG, the correction to the tree-level subleading soft vector comes in the following form. There's an infrared divergent 1/epsilon term that corrects it at one loop. And what they've shown is that it doesn't receive any further corrections in higher loops. Now, this is a little bit confusing because we thought we have pulled out the infrared divergent part by pulling out the pole, the Weinberg pole. But what this tells us is that the loop integrals still have remaining infrared divergences. Now, related to this, in 2018 and onwards, there was a series of papers put out by Ashok Sen and his collaborators, Alok Lada and Biswajit Sahu, who have shown in massive QED and massive scalars coupled to gravity in 4 dimensions, that actually, even after pulling out the Weinberg pole, the loop integrals have a region in the energy space that depends on the soft particle that can be computed to give a logarithm of the soft energy. And they have also shown that this term is one loop exact. Now, although this was a pure gluon graviton amplitude, and this was for massive scalar particles coupled to gauge fields, actually, if you take this log soft vector and take the mass estimate, what you can see is that it precisely recovers the coefficient of the 1/epsilon. So this is a strong hint that what they are seeing here is the remnant infrared divergent contribution to the one loop amplitude that Byrne and al. were seeing in 2014. Now, just to illustrate what it looks like for gravity, the log soft factor looks like this. And beta here is the relative velocity between a pair of particles. This takes a sum over pairs of particles in the external state. And you can see that the form is, in general, much more complicated than the Weinberg factor, or the subleading tree level solved vectors. These contributions usually split into two parts, the so-called classical and quantum parts. And they're named this way because the classical part you can obtain by doing classical computations, clustering, scattering processes. You can recover the classical part. And if you actually compute Feynman diagrams, you find the whole ordeal, the classical plus the quantum parts. This is just to note, the first terms in these contributions correspond to the interactions between matter and gravitons. And the second parts here correspond to graviton-graviton interactions. This will be relevant in the later slides. This new log term that Sen and Sahu have found is called the logarithmic solved theorem. So we have found a new solved theorem, and the correspondence between solved theorems and asymptotic symmetries suggests that this log solved theorem is also the word identity of an asymptotic symmetry. And there were some earlier attempts in trying to write this out. There was papers in 2019 of Campiglia, Lada, and Atul Bakar, where they construct some conserved charge, which if it came from some symmetry, and if you have written down the word identity, it will reproduce the the log solved photon theorem for QED. And then there were later papers by Donay, Nguyen, and Rusconi Agrawal, who study infrared divergent corrections to superrotation word identity. And they find that if you collect all the 1/epsilon contributions, the divergent contributions to the word identity, you recover the log solved graviton factor of Sen and Sahu. But the picture still is not complete because the symmetry in QED is unknown, and the infrared divergent factor still comes from as 1/epsilon. So if we hadn't known that the work of Sen and Sahu, in the sense that there's a new solved theorem that goes like logarithmic in the energy, then we wouldn't have guessed that there is a log solved theorem from this way of approaching. And in this talk, I would like to convince you that you can actually derive the log solved theorem from the symmetry point of view. And how you do this is by just taking long-range interactions of the gauge field properly into account. And for concreteness, we'll consider superrotation in a theory of massive scalars coupled to gravity. But a similar story follows for massive QED and massless QED as well. Okay, so since we have massive particles that will asymptote to time like infinity, we will use hyperbolic coordinates, which are well suited for this. And for people who have looked at space-like infinities, you can think of this as the analog of the Big-Schmidt's coordinates that people use to study I0. This is an analytic continuation of that to I+. And in these coordinates, a superrotation on time like infinity is generated by the hyperbolic vector field, which takes the following form. So you have a vector field on the three-dimensional hyperboloid, which is mapped from the vector field on a sphere that generates superrotations, and is smeared by an ADS3 vector bulk to boundary propagator in Euclidean signature. And this is natural because these hyperbolas can be thought of as an ADS3 slicing of Minkowski in the future light cone in the Euclidean signature. Now, what people usually assume when we talk about asymptotic fields is that interactions vanish at infinity, and therefore we can approximate fields to be free. But now it is well understood that this is not true for gauge theories. And there are long-range interactions. So what we do is we take free fields, we plug them into equations of motion, and then we compute the first-order corrections that come from long-range interactions. We plug it back to the equation, compute the second-order equation, and so on. So we can do this perturbatively to all orders. And what we find is that the graviton field actually exists at time like infinity, and it is completely sourced. It's given by the creation annihilation operators of the scalar field. And because of this graviton field, the solutions to Klein-Gordon equation in curved background, flat plus the graviton field, is no longer free. It, at leading order, develops a divergent phase. You can see that there's a log of time here, and time goes to infinity. And then there are some subleading terms, which is necessary for this analysis, but unfortunately, there doesn't seem to be a nice way in which they exponentiate. And now, using these asymptotic fields, we compute the superrotation charge on I+. And what happens is that the charge is divergent as logarithm of time. And we have to regulate this by introducing an infrared energy scale that we call lambda. And because we have solved the equation to all orders in the coupling, and this term here is, as far as the coupling constant goes, it's this one loop in the coupling. And therefore, this can be thought of as a derivation that the charge is one loop exact in the coupling. Now, the soft charge also gets infrared divergent corrections. And there are two contributions to this. One is that the gravitons, just like matter fields are dressed by gravitons, the gravitons themselves get dressed by gravitons. Of course, you can derive this contribution by solving Einstein equations, but a shortcut to do this is you put a gauge field and couple it to a background graviton, and you'll find that the graviton dresses the photons. And by equivalence principle, if photons get dressed in a particular way, gravitons will get dressed in the same way. And by that analysis, you can find that the usual superrotation charge on that scry gets an infrared divergent correction. And in addition to this, because there are matter fields on I+, it talks to the graviton field at the future boundary of the null infinity. And if you look at the Einstein equations, you'll find that the number of logarithm of time that appear in the stress tensor is highly correlated with the number of log u over log u n over u in the shear that appear in the large time limit. And by computing the stress tensor using these asymptotic fields that we have computed on I+, we find that there is at most one log that appear in the stress tensor. And using this, you can show that actually the shear gets a 1 over u correction with no logs at large times. Now, this could look innocent, but if you look at the soft charge expression here, there's a derivative in u times a u and an integral that goes from negative infinity to infinity. And if you put in 1 over u here, you see that this is infrared divergent. So in addition to this correction coming from graviton-graviton interactions, there is an infrared correction coming from matter-graviton interactions as well. So we again regulate this by using the infrared scale. And you may be worried that you are using the same scale on different charts. So these regulators may not be exactly the same. They could have proportionality constants, but this is fine because we are putting it inside the log. So whatever proportionality constant we had between the chart on I+ and the chart on scry will fall into the finite part when we take lambda to 0. And therefore, the soft charge we can write in the following way. We pull out the log of the regulator, and the coefficient takes the following form here. I haven't written down an expression for H naught RR, but this is also some sourced graviton field that can be written in terms of the matter fields. And again, because we have solved the equation of motion to all orders, and this is a one loop effect, and we find no higher order effects. You can think of this as a one loop exact expression in the coupling. So collecting the results, we find that long-range interactions give rise to infrared divergences in the superrotation charge, and we can regulate it with some infrared scale to have the following expressions. We write down its conservation law in scattering processes, and we find that the word identity, of course, is divergent because the charge was divergent, but we can divide out by log lambda inverse. And everything that was finite in lambda will vanish, and we will have the coefficient of log lambda giving us a finite word identity. And what we find is this. The soft charge gives rise to a graviton insertion with a soft limit with some awkward parameter, awkward projection operator, sorry. And the insertion of the hard charge gives rise to exactly the classical part of the log soft graviton factor. And here we only recover the classical part because in solving the equations of motion, whenever we needed a propagator, we have used the retarded propagator instead of the Feynman propagator. And it's known by the work of Alok-Lada and Miguel Campiglia that if you change the boundary conditions, you can recover the also the quantum part of the log soft vector, at least in QED. So we know that if this works for classical, the classical factors, we know that we can make it work for the quantum vectors as well. This is under still work in progress. Now, what is to be noted is that this word identity has a projection operator. And if you act it on any power series of the energy, it kills any omega to the power n. So if we hadn't known the work of Sen and Sahu, that the log soft theorem exists, from this we can deduce that there must be some non-analytic term in the log soft expansion, in the soft expansion. And you can actually show that if you allow powers of logs, this projection operator precisely picks out the coefficient of log omega. And therefore, what we can see is that the classical log soft graviton theorem can be derived as the word identity of superrotation. So just a quick summary, here's what we have done. We have started from free fields. We plugged them into equations of motion and found the asymptotic form of these fields coming from long-range interactions. And then we compute the charge, write down the word identity, and this naturally recovers the classical log soft graviton theorem of Sen and Sahu. All right, I guess that's it. Thank you.